So yeah, just to remind us of the goal, what we want is basically a way of, I guess, getting an idea of when two variables are dependent in a interpretable sort of way. So these are the pictures that I put up last time. I'm basically trying to find nonlinear mappings of the random variables that I wish to tell are dependent or not, such that there's a high linear covariance. So basically another way of expressing this is like, if there exists a mapping, a smooth mapping of these two variables with a high linear dependence, then it's very likely that these two variables are dependent. So this is sort of the picture that I'm trying to sort of achieve. And I'm going to arrive at something like this by defining a notion of covariance in feature space, and then using that notion to be able to find two functions which have a smooth, two smooth functions such that I can map my variables to have a high linear dependence. So this is my goal. I'm just going to plug this in. Okay. Yeah. So to define covariance in feature space, what I started doing last lecture was to talk about, what it means to have something like a covariance in an infinite dimensional space. So we already found that even defining an expected feature map in an infinite dimensional space, one needs to be a little bit careful. You need to make sure that the expected feature map actually exists and has finite norm, and has the property that, if you take the inner product with this expected feature map, that you indeed, get the expected function. So again, if I'm defining a covariance in an infinite dimensional space, I'm going to have to take a lot of care to make sure that, taking a covariance between two perhaps infinitely large vectors is allowed, is mathematically sort of not too suspect. So the first point that I wanted to cover is basically what space does this infinite dimensional covariance live in? What kind of object is it? And then I'm going to find how to use this object to get these smooth functions that allow me to tell whether variables are dependent or not. Okay. So let's just start by talking about what a covariance is when you have vectors. So let's say I have two vectors x and y, and assuming these have zero mean, what is the covariance between them? Well, it's the expectation of xy transpose. And what property does this matrix have? Well, it has the property that if you take the product f c x y g, so this is a vector, this is a vector, this is this covariance matrix, then you can take these f's and g's inside this expectation because they're constant, they're just vectors, and then you get the expectation of the product of f transpose x and g transpose y. So if you sort of think of f transpose x as being a linear function of x, and g transpose y as a linear function of y, then f transpose cxyg is the covariance between these two functions. So is this, this is just a linear algebra intuition. Now, what if this matrix were infinite dimensional? What I want now is an analog to this property here. I want just something that has the property that the inner product of f and this infinite dimensional matrix type thing acting on G is the expectation of the product of these two functions. So it's the covariance of these two functions. So I want, if G is in some reproducing kernel Hilbert space, and if f is in some reproducing kernel Hilbert space, then I want this property here to hold for this infinite dimensional object. And so I'm going to basically first of all talk about what space is this object in. Then I'm going to talk about how to define it. So and prove that it's in that space. And then I'm going to talk about first of all how to get this maximal covariance. And then I'm going to sort of say, well, what other statistics of this object can be used to determine dependence? So I sort of say, well, you can find these two smooth functions that have large covariance. But maybe there are other ways to sort of analyze this object and find dependencies which are sort of more subtle than just looking for two smooth functions that maximize mean covariance. Okay, so that's the sort of big picture. Okay, so first of all, I'm going to talk about like what space this covariance object lives in. Okay, so because I'm talking about covariances, I need two different function spaces. So I've got now two reproducing kernel Hilbert spaces, f and g. And I need to define a set of basis functions for f and for g. So these are these e's and f's here over some index set. So if the Hilbert space is infinite dimensional, then there'll be infinitely many of these basis functions. And the space in which my covariance is defined is the space of mappings from G to F, okay? So it turns out that this space of mappings from G to F itself is a Hilbert space. And so like, you know, you think of this, for instance, in the linear case. Let's say that G is just RD and F is RH. Okay, so these are just two different spaces. Then L is a matrix in the space of, well, H times D, H times D. Because if you take an H times D matrix and you act on a D-dimensional vector, you're going to get an H-dimensional vector out. Okay, so this is sort of how you should think of this operator here. But you know, we can generalize this notion. So G might be some infinite dimensional feature space, F might be some other infinite dimensional feature space. Then this is a matrix multiplying objects in this feature space and putting out something in that feature space. So this is the sort of picture you should have in your head when you see this thing here. Okay. Now, what you want to be able to do is to take, you know, I'm saying that this is in a Hilbert space, so I need to have definitions of things like norms and inner products for this object. So basically, like, how big is this matrix? Well, one way to do this is basically like to take the sum over all actions of this matrix on every basis function in the G space. So this is like, you know, an infinitely many functions, I guess, one for each fj, and then take the norms of each of these. So this is like a sense of how large this object is. Like you project it onto every basis function, and then you take the norms of all those projections. Okay? And likewise, you can take the inner product of two such objects. Okay? So, you know, what's the inner product? Well, what you could do is you just take this matrix, you project it on each of the basis vectors, you do the same for that, and then you take the standard inner product between these two projections. And this is an inner product between these two matrices, okay? And you can do a little bit of algebra and show that, you know, if you take this inner product and you take the inner product of L with itself, then you get exactly back this norm here, okay? So my covariance operator is going to be an object in this space here. It's going to have this inner product, it's going to have this norm, okay? So remember that when I talk about covariance matrices, it's always something like the expectation of xy transpose, okay? So now I need to generalize this notion of xy transpose to infinite dimensional spaces. So again, like here is some notation which I'm going to explain in terms of linear algebra. So let's say that A is in RD and B is in RH, say, and let's say G is also in RH. Okay, so if I was doing linear algebra, I could say that A B transpose, which is a matrix. Okay, so this is a D times H matrix, acting on the vector G is just equal to A times, I'll just write it like this, B transpose G. Okay, so what I've written up here is just precisely what I wrote here, but just with notation that is also holding for infinite dimensional spaces. So let's say that A is in some infinite dimensional RKHS, B is in some infinite dimensional RKHS. Then when I write this A Kronecker B, what I mean by this notation is exactly the analog to this A B transpose thing. So this is just a sort of, A B transpose notation, and then the action of this object on some other function, which is in the same space as the B, is just the inner product of G and B acting on A. So you can see that this is in the space of mappings from the G Hilbert space to the F Hilbert space, because I take a function in from the G Hilbert space, and I get out a scalar times a function in the F Hilbert space. So this is, an object in the right space. So is that clear? Okay. So first of all, like I've defined my A-B transpose, I need to make sure that this object has finite norm in the space that I defined in the previous slide. Okay, so I want to make sure that it's in, like, this A-B transpose for infinite dimensional vectors is in fact in the space. So to do that, I can do a very simple proof. What I want to do is to take the norm of this object here, and I want to determine under what conditions this outer product has finite norm. Okay. Now remember, on the previous slide I defined the norm as being the action of this operator on all the basis functions. So this is like a stack of outputs. And you take the norms of all of these and you sum them. Okay. So this is a notion of how large this operator is. Now we know what A cross B acting on F is. It's just the inner product of B and F multiplied by A. That's just my definition, which I put up here. Okay. Now, this thing here is a scalar, so I can take it outside the norm. That's what I've done here, So I've got like the norm of A and then this scalar, and I take the sum of these scalars over all of the J's. Now, by Parsifal's identity, this thing here is just the norm of B. Okay. So what I've shown is that the norm of this tensor product is just the product of the norms of each of the guys that define it. All right? So as long as each of these have finite norm, then this has finite norm. So this is a quick way that I can check whether A tensor product B is in this space that I want to define my covariance operators in. I just say, well, does this have finite norm? Does this have finite norm? If so, then this thing here has finite norm. Okay? So this is my first step. Now my second step is, like, I want to have something that when I define my covariance operators, you remember I wanted to have something that looks like this, right? F C x y g is equal to the covariance between f of x and g of y. Okay? Now to do this, I need to say, what's going to happen for some operator in the Hilbert space that I've defined, gf, okay? What happens when I take a function in the f and I take the inner product with such an operator and a g? Okay, so what does this look like in terms of operations on this space here? And the answer is basically this expression here. So if I do something like a object in my Hilbert space B, then this just looks like the inner product in my Hilbert space of this L function and this tensor operation, okay? So this, this means that I can now basically write this operation here, which is what I sort of want to show, in terms of an operation in my tensor space. So this I will just do on the board. So it's worth understanding what's going on to prove this, because it tells you quite a lot about what's going on with how these operators work. Okay. So I've got, let's start with this inner product, L, A, B. in the Hilbert space. Okay, so what does this look like? Well, we've said that the inner product is sum over J in J of L F J and A B F J. And this is taken now in the F space. So this is my definition of an inner product. Okay. Now let's say that the action of L on Fj, so this gives me a function in my F space. I'm going to say that the action of L on Fj can be expressed sum over I in I of alpha J I E I. So what does this mean? This means that if I take my operator L and I make it act on a basis function in the G space, this gives me a function in the F space. And I'm writing this function in the F space as a linear combination with weights alpha, and I put the J here because it's the Jth vector here, of the basis functions of the F space. Okay, so I'm just basically summing up a weighted sum of the basis function of the F space. And like any function in the F space can be written as this sum. I'm just doing it for one particular function. Okay. So let's write that down. J in J. So now LFJ. So what's that? That's just sum over I in I, alpha I J E I. Okay. Now, by definition, A cross B Fj is just A and the inner product of B and Fj. Okay, that's a scalar. And then this whole thing taken in the space F. So the BFJ is taken in the space G, because that's in the G space. Okay, and so now what is this equal to? Well, we've just got a double sum, J in J, sum I in I of alpha I J, alpha. And then you've got EI, AI, EI, AI, and then B, FJ. Okay, so if I write this down, this is the expression I get out. Okay, so now this is one side. Now let's see what happens when I write this one down. Okay, so I'm going to keep the final point here, but I'm going to erase all of the stuff above it. So what happens when I now write A, L, B? Okay, so this is equal to so first of all, let's write, how do I do this? Right. So if LFJ is this, then LB can be written as, okay, let's start with this way. If I have a vector B in my F space, I can write this as B is equal to sum over the inner product of B, Fj, Fj. Okay? And this is sum over J, J. So what have I done here? I've just represented this vector B in my F space as a sum of the projections of B on all the basis functions acting on the basis functions. So this is like it's a sort of like a way of expressing B as a linear combination of all of these basis functions in the space. Okay? Which, you know, you can always do that. Like, it's, if you had a vector, it's sort of saying, well, my vector has components in each of the coordinate axes. I'm just doing that in the infinite dimensional space. Okay? So if I've written B like that, then what is LB? Well, I know what L acting on each of these functions is. Okay? And so now I just take the sum over that. So this is L acting on sum over J in J, B, F, J, right? And we know that this is equal to, well, L acting on Fj, we have that. So you've got J in J, B, Fj, and then L acting on Fj, which is sum over I in I, alpha I, J, EI. Okay. So this expression here is just L times B, where B, L acting on B, where B has this expression here. Okay, so let's substitute that in. This is inner product of A and L acting on B, which is sum over J in J, B, F, J, and then I in I, alpha J I, E I, inner product. Okay. So now this is equal to, so this is a scalar. The only thing that's a element in a function space here are these EIs. So you've just got sum over I in I, alpha J I, A E I, and then you've got also the sum over the J's, and then you've got the inner product of B and Fj. So you'll notice that these two things are in fact the same, which is as it should be. So this is how you can sort of do these kinds of proofs and show that, well, this thing here is equal to that. Okay? So you'll notice like there's nothing terribly difficult about these proofs. Like all that I do is basically like write everything in terms of the basis functions of my F and G space, and then it's like some very, very straightforward algebra. So all of these proofs are in the notes, but like this is just to sort of give you the idea. Okay. All right. So I've defined a tensor product, A cross B. Now I need to define a covariance. So a covariance is a expected tensor product, okay? So I'm going to define my covariance as just being the expectation of the feature map of X crossed with the feature map of Y. So it's exactly what you would expect the covariance to be. It's just like the expected tensor product of X and Y, but in infinite dimensional spaces. Okay? So the difference with respect to what I've shown in the previous slides, like in the previous slides, these were just fixed elements in the feature space. Now these are random variables. So again, just as in the maximum, just as in the mean embedding, I need to make sure that if I take these objects here, and for instance I take their expectation, this object has to also be in the Hilbert space that I've defined a functions mapping from G to F. Okay, so I want to make sure that this thing here is in the space that I'm using. Okay, and if it is in that space, then I can show this property that I'm after using the proof that I did on the previous slide. So my question now is, how do you prove that this object here is in this space? And the idea is that, like, if this thing here has finite norm, then we know it's in the space. Okay. So actually, yeah. What do we do? Okay, is this stuff? So okay, what I want to show is that there exists some element in the Hilbert space, x, y, such that if you take the inner product of this guy with another element in the Hilbert space, I'm going to get out EXY of this tensor product and A. Okay? So this covariance operator is going to be something which has this property. Okay? Now, remember from the Riesz theorem that if, let's define an operator at Txy, okay, which is from the space HS, GF to the wheels, and let's say that Txy is exactly something that takes this operator A and maps it to EXY of Tx plus Y A. Okay? So we want to basically say, like, can this operator here be written as an inner product in this space? Okay? So can I take this thing here, which takes an A and puts it into an expectation, can I write that as an inner product with something? And if you can write it as an inner product with something, then this something here is the, like, you know, is well defined. It is the covariance operator. So the way that we do this is basically using the Riesz theorem. So it basically is Txy bounded operator. So what does that mean? That means that Txy acting on the operator A should be less than or equal to some lambda times the norm of A in the Hilbert space. Okay? And I should put actually an absolute value around here. Yeah. Okay, so if this is true, then I can write this operation here as an inner product with some element. Okay? So this is what the Riesz theorem tells me. So this is exactly the same theorem that I used to determine whether the mean embedding existed. Okay? But now I'm using it to determine whether the covariance operator exists. So this is the difference. Okay?
What does the lambda depend on there? Can it depend on A?
The lambda must not depend on A, that's the trick. Yeah, so the lambda, I've just written xy here because it's depending on the operator xy, so the distribution, but it cannot depend on A. Yeah, so that's very important. Yeah. Okay. So let's see if you can do this with this operator. Okay. So let's write down Txy acting on the operator A is equal to absolute value E x tensor. Actually, I'll use a different feature space for y, but this is not important. Y A. Okay. Now using Jensen, I can take this expectation outside, EXY, absolute value of inner product of the x tensor y A. Okay, next step, using Cauchy-Schwarz, less than or equal to EXY. Now the norm of the x tensor cy times the norm of A. Okay, we've got the norm of A already coming out. And this is equal to, well, you've already got this answer here. So if this thing here is my lambda xy. It only depends on x and y, it doesn't depend on A. Okay? So we're done. So it's bounded, so that means that I can write Txy as inner product of Cxy and A. Now the problem is that the expectation of the norm of a tensor product between infinite dimensional vectors is kind of not very nice. So I've just said, like, if some condition that I don't understand holds, then my CXY exists, and that's perhaps not very useful. I want something that I can actually test. So let's see how we go with this. So remember that the norm of the tensor product is just the product of the norms, okay? So I've got now this norm, phi x, phi x tensor cy is just the norm of phi x, right, times the norm of phi y. Okay, so what is the norm of the feature map of x? What is the feature map of x in a product with itself?
Kernel XX.
Yep. And then let's call the kernel of YL. So I have like different kernels. Kernel Y, Y. Okay? And you need square roots. Yep. So basically, if the expected square root of the product of the kernels is bounded, then my CXY exists. Okay? So, you know, this is a pretty simple condition to check. Like, for instance, if my kernels are bounded, then their expectation is always going to be bounded. So, you know, it's actually reasonably difficult to make a case where this doesn't exist. In the same reason that it's reasonably difficult to make an example where the mean embedding doesn't exist. And, you know, as long as I'm using bounded kernels, I'm never really going to get into trouble with this thing. Okay. So I've shown that my covariance operator exists, and it has this property here. Okay, so last of all, what I need to show is this property that you can get covariances. So here's the very last property. Remember what we wanted to show? We wanted to show that f of Cx yg is equal to, and I'm going to assume that everything's centered, the expectation of f x g y. Okay. So what's this? Well, a couple of slides ago we showed that this is equal to the tensor product of f cross g and cxy. That's the thing we did that very laborious proof of. Okay. Now, what's the definition of the covariance operator? Well, this is the thing that takes the expectation over x and y of f cross g and phi x cross phi y. Okay? This is the definition of the covariance operator. We showed that such an operator exists. Okay? Well, now using again, you know, the inner product between two tensor mappings, what we have is EXY, and now we've got inner product of F and Gx and G. Let's make a different feature space for Y again. C Y. Okay? And that's exactly what we want. F, X, G, Y. Okay? Did I? Yeah. Actually, what I should do, I will add some more steps to that, because let me put in just one more step here. to make it completely clear what I'm doing. So remember this trick here, ex, y. Now the inner product with this, like this is this case here, right, where you've got f plus g and L, right? And this is the thing that we saw a little bit earlier. So I just want to make that clear. Okay, so this is the inner product of f and phi x plus cy, right, acting on g. I mean, I just want to add that step because otherwise I've skipped too many steps. And then we know what this is, right? This is the expectation over xy of f, and now we've got phi x multiplied by g and cy, right? Which is what I wrote before without skipping as many steps. F cx g cy is equal to the expectation of f x g y. Okay, so I hope this is clear. Yeah. So all of these proofs are in the notes, but yeah, that's how it works. So we have defined a covariance operator, and we have shown that it has exactly the property that we want, and we have shown that it exists. So we now have all of the tools that we need to use this thing now to like find dependencies between x and y. Okay, so that's like, yeah, like a reasonable amount of math, but it's, I think, useful because it's showing like that we're not doing anything that will us up later, particularly in infinite dimensions where things can go a bit haywire. Okay, so these are all the proofs. Okay, so now let's go back to our example. We want to find these smooth functions that have a high linear dependence. So remember what it is that we were looking for. We were looking for functions which are smooth. So I'm putting a constraint here, the same constraint that we were using for maximum mean discrepancy, but now I've got two constraints rather than one. So I've got the constraint that this mapping here has to be smooth, but also that this mapping here has to be smooth, okay? And then I'm maximizing with respect to these smooth functions the covariance, and here I'm including the centering term, between f of x and g of y. Well, we know actually what this is for reproducing kernel Hilbert spaces. This is just the inner product of f and the covariance operator with g, okay? So we have an object which we can use in this expression. Now let's say that, you know, as in the assignment, somebody gives me a whole bunch of samples from x and y. How do I actually go about computing these functions, and how do I go about computing this covariance? Okay, so this is the topic of the next slide. So if I have samples from x and y, what's my linear covariance? Well, this is just the empirical expectation of the tensor product. So basically you take the sum over all of the samples, and you take phi of xi tensor phi of yi. Okay? And because of the centering term, you need to subtract off it the mean embedding of x tensored with the mean embedding of y. Okay? So this object here is the empirical estimate with centering of the covariance operator. So these terms here are just so I can get the expectation of f times the expectation of g. And I think it's in the assignment that it's a worthwhile exercise anyway, like to convince yourself that this thing here, which is a covariance operator with centering, is going to correctly give you this expression here, okay? So it's using exactly, like it's not much more math than the math that we've seen already, okay? So I'm going to now define a very concise notation for this, which is at least somewhat, I guess, an abusive notation. But anyway, what I'm defining here is like an infinite dimensional covariance operator, but I'm defining it using a sort of linear algebraic notation. So if these x's, if this x matrix here had in its columns just a bunch of like d-dimensional vectors, and this had a bunch of h-dimensional vectors, then this is my standard equation for the covariance between x and y. So this H matrix is just the unit matrix minus n inverse times the matrix of all ones, okay? So this is like, in whatever standard textbooks, like the covariance between the x and y matrices. So I'm going to be a little bit bad with my notation and say, well, let's just say that this covariance operator I'm going to write in the same way. So I've got stacked in my columns of x these infinite dimensional feature vectors. So this is an infinity by n matrix. And I've got, y stacked the same. And then I define my covariance operator in exactly this way. And this is going to give me precisely, like this equation and this equation are identical, just as they would be for the linear algebra case, okay? So this is my covariance operator. I've got now my kernel matrices, so like, given that I've used this pathological notation, then I can write my kernel matrix as the x transpose x. So each entry in that matrix will be like this infinite dimensional vector interproducted with another infinite dimensional vector, which is then like the ijth entry, and likewise for L. So is this notation clear to everyone? Like, it's kind of weird notation because I'm sort of writing an inner product between things which have infinite dimensions in one coordinate, but like nonetheless it's the same as one would do for standard linear algebra. Yeah. Okay. Okay. So now using my covariance operator notation, what I want to do is, well, precisely what I've written here, to maximize the covariance, like this thing here, which is the covariance between f of x and g and y, computed empirically, so computed with this empirical covariance operator, subject to these two smoothness constraints, okay? Now, just as in principal component analysis, I can expand my f and my g as linear combinations of the basis functions, okay? So for instance, I'm writing my g as a linear combination I of beta I of, now here it's a little bit tricky, phi of xi minus mu y, phi of yi, I should say, sorry, yi minus mu y, and that's empirical, okay? So basically I'm saying that my g function must be a linear combination of feature mapped y samples minus their empirical means, so they have to be centered. And the reason for that is because, remember, my cxy was equal to the sum 1 on n phi xi minus centered, like the centering term, tensor producted with cyi minus the centering term. Okay? Now remember, if I take this operator here and I make it act on another function, I get basically like a sum of these guys here interproducted with g, okay? So if, let's say that I had g is equal to this term plus g perpendicular, which is basically something that can't be written as this linear combination of centered points. Well, if I take this thing here, which is phi of yi minus the centering term, mu y, okay, from here, and if I take the inner product of this with g perpendicular, this is going to be 0, okay? So basically, like any component of g that can't be written as this sum, as soon as I hit it with my covariance operator, it's going to disappear. So basically, like, there's no point in including anything else here which can't be written as in the span of these centered y's, okay? So this is why I am sure that my g function, has to be a linear combination of the centered columns, okay? So I'm going to use these things here. And now I'm going to basically, so I guess most of you have done some machine learning courses, so you've encountered Lagrangians before as a way of, yeah, most people have, everyone has, good. Okay, so I'm going to now write a single expression, which is going to sort of be maximize this subject to these two equality constraints. So I've got this maximize this, and then I've got a Lagrange multiplier times this thing here, which is for my first equality constraint, and a second Lagrange multiplier for my second equality constraint. Okay, so now this is what I want to solve to get my my constraint covariance. Okay, so now we have some more math. Okay, so first of all, let's just look at this term here. What does this look like? So I've got my norm of f in f squared. So what does this look like? Okay, well, I know that f can be written as xh alpha. So using my slightly dubious notation, what this looks like is basically norm of f, the inner product of f in itself. Okay, and so I'm going to basically, let me write, just so I don't have to write the big thing a lot, Pi is equal to the original mapping minus the empirical mean. Okay, so this is equal to sum over I, alpha I, phi xi, with a tilde, so it's centered. I, alpha I, phi tilde xi, right, which is alpha I, oh, alpha transpose. Actually, let me write the sums out. I, j, alpha I, alpha j, k tilde, xi, xj. So k tilde is my kernel matrix between the centered points. And this is equal to alpha transpose k tilde alpha. Okay, so this is what this norm looks like. Now, again, you can do some pretty straightforward algebra to show that this k tilde, I'm going to write it up here, is equal to h k h. Okay, so this is something you can write in a couple of lines, but I will leave it, I think, for the assignment. Okay, so this is my f, this is my norm of f. So next thing that I need, so let's just write that down here. F squared is equal to alpha transpose k tilde alpha. Okay. Now, what is f c x y g? Okay, so I'm going to basically here use, I guess, shortcut. Sum over I, alpha I, dxi, right? And then you've got sum over j, and then you've got xi, oops, tensor c yj. Okay, so this is my empirical covariance operator. It's just the sum of the tensor products between the phis of the x's and the phis of the y's. Okay, these are all centered. And then I've got, so that thing here, I'm going to write as c x y hat. And then I've got my g function here. So what is my g function? And sum over L of beta L, oops, L of tilde of y L. Okay.
Is there a 1 over n?
Sorry, is there?
So is there 1 over n?
And there is, yeah, 1 on n somewhere. Let me put the 1 on n out the front. 1 on n. Yeah. Yeah. Good. Okay. I'm just wondering whether this is making sense. There will be, yeah, quite a bit of algebra going on here, but I will write it out. At least, okay, let's start with just this term here. Okay, so what you're going to get here is basically sum over j of d xj, and then sum over L, beta L, times d yj and d yl. Okay, these are all kernel matrices. And this is equal to sum over j v tilde xj times, so these are the inner product. So I've got the L matrix centered times beta. Okay. And then I take the jth entry. So this is a vector, and I take the jth entry of that vector. So is that clear to everyone, what I've done in these lines so far? Okay, so this is f cxyg. So this is my f function. This is my covariance operator. This is my g function. So let me just take only this part. Is this permanent? That is permanent. This is not permanent. So I've taken just this part here. Okay. And I've used my normal trick that A tensor B acting on C is A times inner product of B and C. Okay. So here I've got A tensor B C, and then I've taken the inner products of these terms here, which is what I've got here. Okay, then I've got, this has to be summed over beta, so I've got my sum over beta. Then this thing overall has to be summed over j, so I've got my sum over j. The inner product between the feature maps of y is just the kernel on the y's, so this is this kernel matrix times the vector beta. And then I've got this, so this is for every j, I've got this matrix vector product. Okay, so that means that I have L beta, which is this term here, multiplied by phi of xj. Okay. Now I am running out of space. So I'm going to just take this and substitute it back in, since we only have one whiteboard. So let's put this back in here. You've got sum over j of d tilde xj times this thing here, L beta j. Okay, so I've just taken this and I've put it back into my sum here. So now I can erase all of this stuff. So what does this thing here look like? Well, I've got my, these are just like, a sum of these guys here with coefficients L beta j. This is a sum of the same terms with coefficients alpha I. So if I multiply this out, what do I get? Well, I get a whole bunch of kernels between xi and xj scaled by alpha. So I've got basically like alpha transpose, then I've got my k tilde, which are these inner products here, And now I've got my L betas, so I've got L TLD and I've got beta. So if you do these products, you get that out. Okay? So what I've shown is that if I have assumed that f and g are linear combinations of centered x's and y's, that this f c x y g with a bit of algebra can be written entirely in terms of kernel matrices on these centered points, which are here k and l. Okay? So there's a lot of algebra, but none of it's difficult algebra to find this. Okay? So I've got my f c x y g, which is this term here. I've got my norms of f and I've got my norms of g. So if I do that, what does my Lagrangian look like? So here is my Lagrangian now. Lagrangian is equal to 1 on n, alpha transpose k l centered, beta minus lambda on 2 times the norm of f. The norm of f is alpha transpose k centered alpha minus gamma on 2 times beta minus 1 beta transpose L beta minus 1. Okay, so I've just taken these and I've put in all of the stuff that I have figured out so far. Okay? So this is my Lagrangian. Now I need to take the derivative with respect to the primal parameters, which are in this case are alpha and beta. Okay? So let's take the derivatives. Okay, so let's take the derivative with respect to alpha. dl d alpha, okay, which is 1 on n k l beta minus lambda k alpha, and that has to be 0. Okay, take the derivative with respect to the second parameter beta. L d beta is equal to 1 on n, and I'm going to transpose everything. So this is what I'm going to get: L k alpha minus lambda, gamma, sorry, gamma L beta is equal to 0. Okay, so I've just taken the derivative with respect to beta, and then I've this is equal to a 0, but it's a row vector, so I've taken the transpose, which means that Kernel is symmetric, but I swap the order because I've transposed it. Okay, so here are my two equations, okay, that I get from differentiating with respect to the primal parameters, which are alpha and beta. And we know from our Lagrange theory that when we take the derivative with respect to these parameters, these have to be 0 at the optimal solution. So the solution that maximizes the constraint covariance. Okay? So first of all, there is a cute trick to be done. Let's multiply or pre-multiply. I'm going to do this in a different color. So let's say we pre-multiply this by alpha transpose and pre-multiply this by beta transpose. So what do we get? We get 1 on n alpha transpose k l beta minus lambda alpha transpose k alpha is equal to 0. And then I've got here 1 on n, and then we've got beta transpose L k alpha minus lambda beta transpose L beta is equal to 0. Okay, so I've just pre-multiplied this one by alpha transpose and this one by beta transpose. So is that clear how I've got to these equations? Yeah? Now, this thing here, I know that this is just the norm of f. And this thing here, I know this is just the norm of g, right? And these things are both equal to 1. Okay, this is gamma. And then these terms here are the same in both equations. So let's say that I just subtract this line from this line. What do I get? I get minus lambda plus gamma is equal to 0. So what I've just shown here is that lambda equals gamma. Okay? So both of these parameters here are equal to each other. I can show that very simply. Okay? So let's remove this and put in lambda. Okay? So I've got lambda here and I've got lambda here. Okay? So that means that using this trick, I can write this whole thing as a single generalized eigenvalue problem. So let's just arrange everything now into a single big matrix. Okay, so what have I got here? I've got a 0 here. I've got 1 on n k tilde l tilde. I've got 1 on n l tilde tilde. Another 0 alpha beta. And that's equal to lambda times k tilde 0 0 l tilde and alpha beta. I'll move out of the way. So this is a generalized eigenvalue problem, and if you basically now maximize this with respect to the lambda here, or you find the largest eigenvalue of this problem, then that is my constraint covariance. So now I found an eigenvalue problem that I can solve to obtain the constraint covariance. And it's entirely in terms of the centered kernel matrices on my observations. So is that, yeah, fruitful? So this is the equation that I would sort of plug into MATLAB to get my solution. Okay. So all of this is repeated here. So as I said, like everything is in the notes. I'm just showing you on the board. So here is my eigenvalue equation. Okay, if I solve this, the maximum eigenvalue is exactly my constraint covariance. Okay. Good. Yeah. So what else? Yeah, and now my f function is just like, you know, here is my alphas and betas, and I can just plug in my alphas and betas, and then I get, you know, these are to evaluate f at x. I take the inner product of my, you know, centered feature maps at xi with the new x point, and this is my function evaluated at x. Okay. So yeah, so these functions here are the functions that maximize the covariance. Yeah. So I'm now going to give, I guess, a sort of interesting question. So let's say that x and y here have this density function. So like red is high density and blue is low density. So here is like samples from this 2D density function. And then here is a case where x and y have I guess, a very high frequency dependence. And so I've sampled from this. So as in the MMD, you would expect a smooth density to have a higher constraint covariance than the rough density. Okay? So what I'm going to plot on the next slide is basically like I've got this density and I'm increasing the frequency of my sort of perturbations. And here I'm plotting the constraint covariance computed with 200 samples as a function of the frequency. And you can see that as the frequency is increasing, the constraint covariance is dropping. So just as I guess an intuition for this, I'm going to go back to the case of the maximum mean discrepancy. So remember, for the maximum mean discrepancy, we were looking for a function which had bounded norm, which maximizes the difference in expectations. So it's sort of saying like, I want a smooth function that pulls these expectations as far apart as possible. Now, if the difference between P and Q happens at low frequencies, then the smoothness constraint doesn't prevent me from having a very sort of large function here and a very small function here. Whereas if the difference between P and Q occurs at very high frequencies, then I basically can't move very far up on these red points, and I can't move very far down on these blue points. Okay? So going back to this example here, remember that we're looking for a smooth function on this axis, which has a high linear covariance with a smooth function on this axis. Now, if the x sort of goes high and low at a very low frequency, so if the dependence is encoded, I should just say if the dependence is encoded at a very low frequency, then these smooth functions can create a very high linear covariance. Whereas if the dependence is encoded at a very high frequency here, basically like a function that takes these points here and maps them to something that looks like a straight line, it's very hard to get a smooth function that does this. So you can sort of push them slightly towards a straight line, but the smoothness constraint sort of prevents you from moving them very far. So this is sort of like an intuition for why it is that the constraint covariance is low when the frequency is high. So yeah, is there questions about this idea? I mean, this is quite a sort of subtle concept, I think. But the idea is very similar to the maximum discrepancy, that because you have smoothness constraints, you're not able to move the points very far if the dependence is encoded in high frequencies. So, yeah. Okay. Okay, so this is the constraint covariance. What you might now ask is, like, given I've got this covariance operator, is there something I can do that's better than the constraint covariance? Because in a sense, like, the covariance operator is an infinitely large matrix of all dependencies between all possible features of the variables. But I'm just using this to get two functions that distort my points to have a high linear dependence. So is there more that I can say about these points using the constraint covariance? Okay, so here's like an example that I've used, I guess, a few times before, where x and y have this sort of dependence, even though if you type the correlation into MATLAB, it's 0. So they're sort of arranged in such a way that their dependence is only encoded in high orders. Okay, and just as in this ring example, like if you map x by this smooth function and y by this smooth function, you get something that looks a little bit like a straight line. Okay. So let's now imagine that we take functions that maximize the covariance, but are orthogonal to these two functions. So I have to say, like, my mapping can't look anything like these two functions, but it should still give me a straight line. Okay, so what do they look like? Well, these two functions are orthogonal to the two that I looked at the previous slide. And if I map my points by these two functions, well, obviously it's not as close to being linearly independent as the best two functions were. But there is still, if you look at the correlation, it's high enough that it is significant. So these are two functions that capture a dependence that was not captured in these two functions. But nonetheless, it tells you something about how the variables are interacting. Okay? So, and why stop there? Like, maybe then you can get the third functions that are orthogonal to these two and to the first two. Yeah, and they can capture some even like more subtle dependence and so on and so on. Okay? So ideally what I would want is a summary statistic of all of these different modes of dependence between my points. And if I can sort of summarize those, then this will be a more general measure of dependence than just looking for the two functions that maximize the covariance. So one summary statistic is just to take the sum of the squared dependencies. So this is, I'm going to call it the Hilbert-Schmidt independence criterion, and the reason I'm calling it this is because it's just the Hilbert-Schmidt operator, Hilbert-Schmidt norm of the covariance operator. Okay, so we've seen what this norm looks like before. If you take the Hilbert-Schmidt norm this is the sum of the squared singular values. Okay, and so this basically encodes all of the possible dependencies between x and y from all of these sort of smooth functions that maximize covariance. So this thing here is a lot more powerful than just the constraint covariance. And if you use it in a test, it's going to give you actually, like even in practice, like a much more sensitive test. Okay? So what I've written here is the expression for the constraint covariance. So I'm going to show you how to get that. It's actually pretty easy. Okay, so let's just forget about all of the centering terms and pretend that our covariance operator is just, this expectation of the x tensor cy. Okay? So, forgetting about the centering terms. So now what we have is cxy, inner product. So that's the squared Hilbert norm. Okay, so what do we know about the covariance? Well, this is the expectation over x and y of cxy and phi x tensor phi y. Okay, so I've just replaced this covariance by its definition. And then I've got another covariance here, so now I've got exy, now here, exactly as when I computed the maximum mean discrepancy, I need to take independent copies of my x's and y's because the random variables for this covariance are independent of the random variables for this. So it's like expectation of tensor product, expectation of tensor product. So I can't take the expectation of the products and say it's the same as the product of the expectations, because that's just not true. Okay, so I need to basically make sure that I maintain the independence of the variables from this and the variables from that one. Okay, so now I've got, this is for the independent copies. And now I've got my one from up here, x tensor y. Okay, so I know how to do this tensor product. This is what I did earlier in the lecture, so that I'm not going to show all of the intermediate steps. I'm just going to say that this is x, y, e, x dash, y dash. And then I have here the inner product of phi x dash and phi x, and the inner product of phi y dash and phi y. And this is just the expectation x, y, expectation x dash, y dash of the kernel between x and x dash, and the kernel between y and y dash. Okay? So this is exactly this first term here, expectation of x in a copy, y in a copy, kernel x and x dash, kernel y and y dash. Now if my covariance operators are centered, then I've got all of these extra terms in there, which you can sort of do on your own, but the proof is precisely like this style of thing. So like nothing is changing compared with what I've written here. It's just like, yeah, expectations in different places. Okay? So is it clear how I've got that this is the norm of the covariance operator? Okay? So this is a nice statistic, well, not only because it captures a lot more dependence than COCO, but it's also way easier to compute. So for constraint covariance, I had to solve an eigenvalue problem. For this, I just type like a line of MATLAB and I'm done. Okay? So this is like way easier than constraint covariance as well. What I guess it isn't is necessarily as interpretable, because when I got the constraint covariance, I had these functions that I could use to map my variables to fall into a straight line. If I just compute this number, like I still don't sort of see how it is that my variables are dependent. So it might still be helpful to compute constrained covariance just to sort of see, what's the kind of mapping that's required to cause it to have a high linear correlation. Okay. Now that's what I just showed. Okay. So this is something that I won't write down because it's a lot of painful algebra, or not painful, but notationally irritating. But if I have a bunch of samples, x and y, and I compute my K matrix, which is the kernel between the x samples, and my L matrix, which is the kernel between the y samples, and then remembering this H matrix, which is like the unit matrix minus the ones matrix, which is my centering thing. Then the empirical estimate of this Hilbert-Schmidt information criterion is just a trace of the K matrix centered times the L matrix centered. So this is like, you can sort of show that this sort of messy expression here, if you actually go and compute this with samples using the sort of same tricks to simulate independent samples of x and x dash that we use for MMD, then you get something that looks like this, plus a whole bunch of terms that are smaller that you can more or less ignore. Okay. So if this is my dependence, then just as in the maximum mean discrepancy, a question that I'm interested in is how do I determine whether this is sort of large enough that it can't be explained by chance. So like, how do I know that this is big enough that I'm sure that there is a significant dependence between x and y? Okay. So to put this more formally, like, what is a threshold that this statistic will only exceed with small probability alpha in the case when there's no dependence? Okay. So if there's no dependence, but this is like really big, then I should say, well, that's unlikely, so I'm going to reject the case that there's no dependence. Okay? So I want to find a way to get this threshold here. Now again, as in the MMD, we run into problems, but these problems are even worse. So when independence holds, what does the distribution of this statistic look like? Well, it looks like an infinite weighted sum of chi-squareds again, just as the MMD did. But this time, the eigenvalues are the solution of a problem that I'm writing here just to show you how awful it looks. And you have to basically take an integral over like quadruples of xy pairs, and it's really, really horrible. So basically, there is, again, just as in the maximum mean discrepancy, no easy way to sort of find the distribution of the statistic. So remember what I wanted to do, just as in the maximum mean discrepancy, like let's say that this is my statistic, and this is my probability of seeing this statistic, given that pxy equals pxpy, okay? And so this thing here is going to be like probably quite heavy-tailed. So basically, like if I generated many, many instances of independent variables, I would get some sort of distribution over dependence statistics, and it's going to have a mean of 0. But it's going to be sort of skewed and so on. Okay, so even though there's no dependence, because of the sort of noise inherent in computing it from data, I'm going to get like a sort of distribution of statistics. Okay, and I want to sort of say, well, what is a threshold t such that it's very, very unlikely that my statistic will be in this region, given that I know that pxy is equal to pxpy. Okay, so this is what I'm trying to determine. And unfortunately, the shape of this statistic here is this really, really horrible thing here. Okay, but there is tricks. So the first trick is that I can actually compute in closed form, despite the awfulness of this thing, the variance of the statistic, and also this expression here, which is sort of the bias, so it's biased away from 0. So one actually very easy way to find this threshold just as in the MMD, and this is what I would recommend you do if you want to use it, is a permutation test. So what we do is, given our data, which is in XY pairs, we simulate the case where PXY is PXY. And the way we simulate this is basically just by taking your X and assigning it a random Y. So if for every X you give a completely random Y, then evidently X and Y can't be dependent, because I've just assigned it some completely random Y from the set of Ys that I have, okay? And then I compute this. And then I do it again, and I compute it again, and I continue and continue. And then I'm going to get basically like a sort of histogram version of this thing here. So if I write here my histograms of all my H6 values, they're going to match up pretty well with this true distribution. So I just keep scrambling my Ys, computing H6, scrambling my Ys, computing H6. I get the histogram, and then I say, well, on this histogram, what is my like low probability region? And then that's how I get my threshold. So is that idea clear to everyone? So it's like really trivial thing to do, and it works. So despite what seemed to be a very tough problem. The other idea is you can just basically fit a gamma distribution and pretend that the infinite weighted sum just has this very simple form, and a lot of the time you'll be lucky and that's good enough. Some of the time you won't be lucky and it isn't. So if you want to be sure that you're correct, use this. If you want to do something fast that might be wrong, use that. That's the short answer. So I guess 2 lectures ago now, I talked about this problem of determining whether extracts from documents in English and French are dependent or independent. So now we have finally gathered all of the tools that we need to solve this problem, okay? So I've got a whole bunch of examples of English and French document pairs, okay? What I've drawn here is my matrix of kernels between individual pairs of English documents, okay? So each spot in this plot is basically the kernel between an English extract and another English extract. So like a dark dot means they're very similar and a light dot means they're very different. The kernel that I'm using here is a kernel on strings, which is basically like counting the number of substrings it matches between these 2 extracts. And substrings up to length 10 in this case. So you can do that. There's an efficient way of computing this with dynamic programming, okay? This matrix here is my L matrix. So this is the matrix of kernels between pairs of French documents, okay, or French extracts, I should say. And I compute my K, I compute my L, and from a couple of slides back, we know that the H6, so the dependence between the English and French documents, is written as the trace of this KHLH matrix, okay? So you can see that this even makes sense intuitively. So basically, like, if a given pair of English documents or English extracts is similar, the corresponding pair of French extracts is likely to be similar. And if a given pair of English extracts are very different, the corresponding pair of French extracts is likely to be different. So if we see this pattern repeated over and over again for pairs of English and French extracts, like similar pairs correspond to similar pairs and different pairs correspond to different pairs, then it's very likely, even intuitively, that the set of English extracts are translations of the French extracts, because you always see this sort of matching of similar to similar and different to different. And what this thing is, modulo the centering matrices, is just the inner product of the K and L matrices, okay? So it's basically saying, like, how similar are these 2 things? And if they're very alike, then it's very likely that the English and French extracts are translations. So is that idea clear? Yeah? Okay. And then I use that permutation trick that I talked about on the previous slide to determine whether they're sort of similar enough that it can't be explained by chance. So this is large enough that it can't be explained by chance. And using this for our example, we were able to sort of find that they're the same. One cute thing is that if you just use kernel, a bag of words kernel, which is just sort of counting the number of words in common between the extracts, then you get a higher error. So it does matter to use a smart kernel on strings and not a dumb kernel on strings. Okay. yeah, I think probably, yeah, it's good to stop now.